Dear colleagues, the talk today is by Michel Carelli, Transfinite version of Mittag-Leffler condition for the vanishing of derived limit. This is a joint talk with Sergei Ivanov. Michel, he is from Technion. Okay, good, Michel.
Ladies and gentlemen, today I'm going to talk about my research about the transfinite version of the Mittag-Leffler condition for the vanishing of the derived limit. It's we have the preprint. It's the joint work with my supervisor Sergei Ivanov. My affiliation is Technion, Israel, and he's right now working in BIMSA Institute in China. Okay. Let's begin. The study of the right derived functor of the functor limit was initiated in the work of Ye, Milner, Ross, and Grothendieck. Actually, first mention was in work of some person called Ye. He was a Milner student, and then other people also used the definition. In particular, it was shown that for inverse sequences of abelian groups, the higher limits, the higher than the first one, are trivial, but the functor lim1 turned out to be not trivial. And then Milner emphasized the significance role of this functor in algebraic topology by introducing what's known as Milner exact sequence for homotopy groups. Also, it was proven at first that if the inverse sequence consists of epimorphisms, then the derived limit is trivial. It's kind of simple fact. And then Grothendieck introduced the Mittag-Leffler condition. It's not that simple fact. That's for this condition. From this condition follows the fact that inverse sequences, the limit of the derived limit of the inverse sequences is vanishing. This condition generalized epimorphism condition. But if all the components of inverse sequence, like all the groups, are at most countable abelian groups, then the Mittag-Leffler condition becomes necessary and sufficient for vanishing of derived limit. But if we deal with the case of non-necessary continuous, non-necessary countable abelian groups, then this condition is not necessary. It's not necessary. So we're trying to find the necessary and the sufficient conditions, so it might be equivalent to the vanishing of the derived limit. Okay, first of all, a little disclaimer about the generalization. Because the same results that I'm going to state right now, they can be proved for any abelian category with generators, small direct sums, and small products, so AB3 and AB4 star. But we're going to talk only about category of abelian groups because, in the sake of convenience, and in that case, I can present to you some explicit formulas that would be better for understanding. Okay, the first definition in the inverse sequence is a sequence of abelian groups. It's a couple consisting of two families. First family, it's AI, indexed by natural numbers. It's the family of abelian groups. And the second family is FI, family of morphisms, from morphisms of abelian groups from AI plus 1 to AI. We call an inverse sequence a null sequence. if for every if every fi is a null mapping. That will be important object later. And another important object, another important class of inverse sequences is epimorphic sequences. The sequence called epimorphic if every fi is an epimorphism. Okay. The next definition, limit mapping. If we have A in inverse sequence, then the limit mapping of A is a homomorphism phi from product of members of A, direct product to itself, defined as follows. So basically, if we take a sequence from this product, A1, A2, so where small ai is from the group BKM. Then the image would look as follows. So we get the sequence and we extract from it also the sequence but shifted by the map F. Okay, you won't find this notion in paper actually in preprint because it can be, you can't define this formula specifically for arbitrary category, but in abelian groups, we have an explicit formula, so it's easier to see what we do. Okay, now the definition of limited derived limits. Suppose A is an inverse sequence and phi is its own mapping. Then the limits can be defined as the kernel of phi. That's why it's called limit mapping actually. So basically, it's like all the sequences such as A1 equals to image of A2, A2 image of A3, and so on. And the next definition is derived limit. It's the core kernel of limit mapping, and you can't get actually such convenient view of derived limit, but if we have if derived limit is equal to 0, it means that limit mapping is surjective. So for any sequence B, there is a sequence A such that it must under phi to B. Here this formula. Okay. Then the proposition, it's actually more of a proposition. The rest of the results formulated here would be our own results, but this proposition is been going for a while. It states that if we have exact sequence of inverse sequences, it means that we have we have some morphisms that's exact in any vectors. So like morphism from AI to BI to CI, this sequence is exact, and for AI, yeah, and there is distributed obviously. Then there is the exact sequence of abelian groups. So here we have three limits and three derived limits. So basically, for example, you have vanished derived limits of A. That means that the factor of limits would be exact, for example. Okay, and to define the use, for example, of this proposition, or generally to demonstrate the idea of derived limit, we can take a look at the following sequence. Defined A defined as in the member I, it will be Pi and Z, and the maps would be just inclusions from Z and PZ and P square Z and so on. And we can write the following short exact sequence of inverse sequences. We have the first sequence would be A, the second sequence is just the sequence of Z with identical maps, and the third one is just a factor sequence. And here it's like inclusion and factorization. And hence, if we have such a sequence, then we can write by this proposition, we can write the long exact sequence of limits. And since we know that limit of Z factorized by Pi Z is Pi integers, obviously, and limit of just the sequence of Z is Z, then limit direct limit of A would be equal to P-adic integers factorized by Z, because the direct limit of sequence of z, so it's vanished. So we left with the lib one of a. Okay, now we formulate the image filtration and the Mittag-Leffler prediction. For any I, natural number, and for any ordinal alpha, we will define I alpha of AI for sequence A recursive. So basically, for alpha equals 0, it will be just AI, and if we define the image filtration for alpha, then for alpha plus 1, it would be just the sequence image filtration. For alpha, it's like the second item. And the last item is we define it for limit ordinal as an intersection of all the previous values of filtration. So basically, it's like descending for each I is descending chain of subgroups, and it's a sum of subgroups of AI. And hence we have definition, then we talk about prediction for like predict. We say that A satisfies the Mittag-Leffler prediction if for every I filtration ik of AI, k here is like natural number, we say because it must stabilize an indefinite number of steps. So it's, it makes no sense to look at Transfinite filtration, just find out filtration, then it will stabilize the correct number of steps. This condition implies the vanishing of lib one, but it's not necessary for if groups are uncountable. Okay, and this like it stabilizes trace must stabilize a finite number of steps, but this number of steps can be their own for each I, so it can be unbalanced. Okay, the next definition is completion. First, we'll define the object that we call A alpha. Like for an inverse sequence A, we'll define, and for any ordinal alpha, we'll define A alpha is just a group of sequence of factor groups A by alpha inverse of A. And for any limit ordinal lambda completion, it's the limit of A beta for beta less than lambda. So basically, we just take the limit of the inverse sequences, just limited in each member. Okay, and here we can say that A is lambda complete if the morphism from A to the natural morphism from A to its completion, its lambda completion is an epimorphism. What does it mean? Basically, it means like lambda completion, the member of lambda completion, it like someone wants excuse me. Like it means that like okay, the member of lambda completion is just the sequence of elements of length lambda, and it's like an element of a beta, and these elements are consistent in the sense they can try to represent some element from any. So we like with each element with each member of this limit of completion, some completion, we say like we become more precise. We say that okay, in the factor class by beta image, our element lies in like in this factor class here. When I factorize my beta image, and like so we became more precise, and then eventually, if like any such sequence represents some elements of A, so it means that the morphism from A to lambda completion is a morphism, then it's called A lambda complete. And also this morphism induces always, not even in the case of when it's morphism from a lambda to completion, because if we have like a morphism from A to lambda completion, obviously the elements, the kernel of this morphism would be like the elements of lambda image. Okay, and when we factorize the lambda image, we get exactly the lambda sorting homomorphism. Okay, I always say that lambda pairs always yeah, I always have map from A to lambda completion, and when I factorize by lambda image, I get the map from a lambda to yeah. And this is actually like the natural map from A to lambda completion. It's built from max to from A to A built to just the factorization. Okay, the direction of the link, this prediction is like the first proposition is going to be the new one that's formulated in the paper, and then the rest of the results we'll see. For any ordinal alpha, there are isomorphisms, so basically like the limits of A alpha and the limit of alpha completion of A would be 0, and the limits of alpha image would be isomorphic to limits of A. Okay, and the last isomorphism induced by the monomorphism, this is just monomorphism, is the inclusion from alpha image of A to A, and there is a short exact sequence of derived limits of alpha image A and A alpha. Okay, the short exact sequence can be obtained obviously because we have like we have exact sequence of limits, but like before the first member of this short exact sequence, we need to have limits of A alpha. But since we know that it's 0, then obviously a short exact sequence. And also by like the box I'll remove right now, I'll give you a sketch why the limits of A alpha and the limits of why a limit of alpha would be 0, for example, is because if you remember the view limit is just sequences of elements such that each element maps to the previous one. Yeah. So basically, it can be checked that if we have such sequence of elements, then each element of the sequence would be in like any alpha image for any alpha. So when we factorize by alpha image, we just lose the whole limit, so it becomes 0. And alpha completion is just the limits of sequences with trivial limits and cislinear U. And then we could say it's also 0. Okay, so then we have the following definition: it's the length of the transfinite filtration. If we have some sequence A, the length of its transfinite filtration, or just the length of the sequence, it's not by len of A. It's the least ordinal, such that for any ordinal bigger than len A, the monomorphism from alpha image of A to len A image of A is isomorphism. So basically, like it's the moment where the filtration stabilizes. So we kind of have filtration, and it's like the static chain of some groups, and when it stabilizes, when it's just becomes when the next subgroup is the previous ones. When we start increasing these groups, that's the point we call the line of A. Okay, and then we have a proposition for sequence L A, the ordinal length of A is well defined, that's what I told you. And moreover, in this case, the last image, we'll call the last image of A is the morphic inverse sequence. And we have canonical morphism, and this induces these morphisms that the derived limit of A is isomorphic to derived limits of A len A, and the limit of A is isomorphic to limits of the last image of A. So basically, like at some point for big enough ordinal alpha equal to len A here, And we can say that our sequence A and our sequence is divided into two sequences. One is like an image, the last image, it represents the limits of the image. Another sequence is the factorization by the last image, it represents the derived limit. Okay. Hence we have corollary for an inverse sequence. The following statements are equivalent. First statement is the limit A is 0, and the second statement is the last image of A is 0. And it's because the last image would be anthropomorphic sequences with the trivial limits, as we know by the last position here, have trivial limit, and hence it will be 0. You check what we can help us to. And corollary, it's for that help if we have an appropriate sequence such that it's limit is 0, then this is 0 sequence. Okay, the next definition that we have is local sequences. The inner sequence called local if its limit and derived limits are 0. So basically, like the limit mapping must be trivial. And now we'll try to explain to you the term local, why is it called local. And now we need to be probably boring definition, but still go through it. Like for general category C and the morphism theta from C prime to C, an object I is called theta local if the map if the map induced by theta from the set of morphisms from C to I to set of morphisms from C prime to I is a bijection. So it's been known that the class of theta-local objects is close with respect to small limits. And we show that the local sequences are theta-local objects for some morphism theta in the category of inverse sequences. And hence, as a corollary, we obtain that this class is close with respect to small limits. We'll use this result later. Okay, the first definition. You can just look at the last line, like is being added to the sequence. Define as follows: we have the first n members of it will be z, and the max will be identical, and then we just have zero. Okay, this is pretty simple sequence. And let's have the following line. I need to explain what's a b in the power omega r. It's just inverse sequences because we have omega r. That's the natural numbers with inverse order, and then we have functors from this category to abelian groups, and just inverse sequences. So, like sequence A, there is a natural isomorphism. The first left hand side is like the morphism from Z and to A, and the right hand side is like the morphisms from Z to AM as a groups. And it's easy to see because if you have morphism from Zn to some sequence A, then this morphism is defined by the image of the last copy of Z. The rest of the copy would be mapped according to this method. So it's like it is morphic to the maps from Z to A. Okay, now we will define the wave. It's like the direct sum of Zi for the on this line. And we'll format the following lemma that we have an isomorphism. Again, we have morphism as inverse sequence from Zy to A. It's isomorphic to the direct product of morphisms from sets of morphisms from Z to AI, and it's isomorphic to AI. The last isomorphism is Carelli, and because like the morphism from Z to AI is isomorphic to AI. And the first isomorphism we have it because like by the previous result we know that morphism from Zn to A is isomorphic to morphisms from Z to AI. And hence we have Z wave is like the direct sum of Zi. So the morphism from the Z wave would be just the morphism from the direct sum is just the direct product of morphisms from the sides. So and this is also And now we'll define the T, right? Psi from Z wave to Z wave, such that we can have this explicit formula here. Yeah, that's the element it has one at place n and zero set out places will be mapped like two elements that has one at place n and minus one at place n, minus one at place n minus one and minus one and zero in other places. And this kind of tricky morphism, but still we can try to see what it means. It means like if we compose this morphism, the morphism induced by it to the morphism from A, B, omega from Z wave to A to itself. Then, and also we will compose it with the isomorphism from the last lemma. It would be just a limit mapping of A. And hence, if the morphism induced by psi is bijection, then the limit mapping is bijection, then the sequence A is local. So, and your sequence A is local if and only if it's psi local object. Okay, and hence we, as we told you, you can obtain the corollary that the class of local linear sequences is closed with respect to small limits. The class of that local object for potentially. Okay, and another thing that the class of local inner sequences is closed with respect to extensions by null sequences. It means that if we have an exact sequence where the first sequence is null and the last one is local, then the middle one is null. Okay. Also, I guess we don't have time for that, but I'll tell you briefly. We have localization, liquidity, and localization and the function from C to P. The nature of information from ID to this function, such that the following formulation is isomorphism, and then T object T is local with respect to this localization if like this and the factor is an isomorphism of the subject. Okay, and the corollary that we also can obtain is that in category of inner sequences, there is localization for which local objects have exactly all local figures. It also can be obtained by the fact that by the last proposition that if it's psi local psi and by the already known result. Okay, and now we look at the main result of the paper is Transfinite Mittag-Leffler condition. It states that for a linear sequence, we have the three equivalent statements. First is that the derived limit of A is 0. The second one is that if we take the kernel of map from A to for any limited lambda, we take kernel of map from A to the lambda completion of A, and we take the limits of such sequence, then this limit will be 0. And the third one is it's like the second one but stronger. It states that for limits of for a limit ordinal lambda, if cardinality of lambda is countable, then the A is lambda complete. Lambda complete, remind you, that means that the kernel of map from A to lambda completion is 0, so not just limits of the sequence is 0, the sequence itself 0. And for the rest of the ordinals of the ordinals, we still need to have the second condition. Okay, so basically, like later we will have the examples that we can say that, for example, you can get a stronger prediction that for any ordinal it needs to be lambda complete, because we have the examples of sequence with trivial derived limits, but that's not lambda complete for some limit on standard that doesn't have the countable penalty. And okay, and I'll try to tell you the idea of this theorem, like from first condition to second. It's kind of obvious because we just write some exact sequence one. That's all. From the second one to the first one, this can be proved by the proof on the suppose to prove that a alpha is the trivial derived limit for any ordinal alpha by Transfinite reduction. And since we know that for big enough alpha, the limit of a alpha would be the derived limit would be isomorphic to the derived limit of a. That means that we proved that the derived limit of a is 0. And if we have from third to second, it's obvious. And from the first to the third one, in that case, it's tricky. We need to we take the lambda, which has countable finality, and we take the sequence formulas that tends with lambda, the countable sequence, and then we using the sequence reduce it to the case where lambda is just the omega of the first order, and then in the case of omega, we'll just prove it explicitly. Okay. The next main result of the paper, another main result, it's like the theorem by the description of the class of local inverse sequences. It states that if we have the class of local inverse sequences of abelian groups, then is the least class containing the zero inverse sequence and closed with respect to small limits and null extensions. So basically, we already know where the proof that this class of local inverse sequences is closed with respect to small limits and null extensions. And now we need to prove that any local sequence can be obtained from the zero sequence using small limits and null extensions. And it can be done like we can prove it also by Transfinite reduction. We prove that we can obtain any for any ordinal alpha, we can obtain a alpha, and then we prove it just with the reduction of alpha. And it's quite long proof actually. It's a detail, but we won't get into the proof. Right now, I want to tell you about the examples. The examples, they are also important. First, let's begin with some preliminaries. First, let me define the sequence S of A, for A here is an abelian group, and S of A is just a sequence of where every member is this group, and the mapping is just multiplication by P. Okay, and now we fix an ordinal alpha. It's another definition. We fix an ordinal alpha, and we define A diamond. A diamond is the set of all infinite increasing sequences of ordinals, also equal strings. The strings of ordinals from alpha to alpha and alpha 1 events, such that it's strictly increasing and all of them less than alpha. And we endow it by the data order. Alpha 1 alpha n is less than alpha 1 prime alpha n prime, alpha prime and prime. If you don't leave, either n is less than n prime or they're equal, and there's a moment such that there's moment m, it's natural number m, between 1 and n, such that alpha m is less than alpha prime, and alpha I is equal to alpha I prime for all I less than m. And it would be well ordered. Okay, so we use the alpha diamond instead, and we'll define the a bit long, complicated definition. We're going to define the group, first of all, P alpha and P alpha prime. So P alpha is the group, it's the direct product of periodic numbers indexed by alpha diamond. And P alpha prime is we can view it as the subgroup of P alpha. It's just direct sum of p numbers indexed by alpha, right? And so we denote by E sigma the standard basis of P alpha prime over ZP, and we consider a ZP model. This is a model of P alpha prime called R alpha, generated by the elements of the following form. And so we define D alpha as the P alpha factorized by R alpha, and D alpha prime as P alpha prime factorized by R alpha, and then we can define E alpha. It would be like D alpha factorized by P power alpha by P power alpha D alpha. Okay, now we have definition, long definition of some group. You may be not following this, but still we define the group E alpha, and now we will state some result about it. Very important result that for any order alpha, either sequence S alpha is the sequence of this is local, and the length of the length of the sequence would be alpha. So, like for any ordinal alpha, we can get the sequence E alpha such that it will be local, but like the image construction would be the length of alpha. So, but the local sequences are not very trivial objects. It have any it could have a length of filtration of any kind, and also another definition that we give this is very helpful. It's a case for the product, maybe a method somewhere in literature. For the K regular cardinal, we'll define that we also have a family of the group. It's by set X. We define K-supported product. It's like the subgroup of we define it as PK of AX, and it's a subgroup of the direct product AX, and this group of elements whose support has cardinality less than K. So, like, basically, for example, if we have the direct product, then it has subgroup direct sum of AX, and a direct sum would be omega supported product, for example, where omega is structured. Okay. Then we have the following lemma. It's pretty long, but you can just the meaning of this lemma is just that this case supported product, it commutes with limits, so it's like product of the limits would be the limit of the product, and another lemma also quite long, but the meaning of it also commutes with derived limits. So the corollary from this lemma says that if we have K irregular countable cardinal and family of local sequences within groups, then the K-supported product would be local, because if all the limits of AX and the limits of AX is 0, then since the K-supported product commutes with the limits and derived limits, if we have this product, then it also would be local. Okay, and hence we have the following theorem. If we take the K regular countable cardinal, and if we take the K-supported product of E alpha plus 1, where E alpha plus 1 we had the definition before that, and I can remind you that E alpha plus 1, if we have S of E alpha, that means that for this sequence, the length would be alpha, and it would be local. And if we have the K-supported product of E alpha plus 1, then if we take the sequence derived by this group, then S, this sequence would be local, but not K-complete for this, the length of this S would be K. So basically it means that we can have the local sequence such that it won't be K-complete for any uncountable cardinal K paragraph. Hence we have also the question is so the question still is there an omega complete inverse sequence of abelian groups with non-zero derived limits? So if you haven't found an example, maybe if you find one, we can well, do the next. Okay, thank you. Thank you for the presentation.
Question, you can ask the speaker, but we answer it immediately. Of course, first we thank the speaker once again. Okay.
Point is that the English construction symbolizes like for each member by English construction symbolizes the finite numbers. Okay. Yeah, okay. The question was I answered that Mittag-Leffler, the sequence satisfies Mittag-Leffler condition if for any member the image reverse stabilizes on a finite number of steps.
Any questions? Theory you mentioned plus minus that the skull constructed sequence is not complete, right? That's the whole thing is the statement, because otherwise you already constructed something that is local, like as exactly transfinite image length filtration. It's not arbitrary.
Yeah,
the alphas are objects which are both local and have a predefined length, right?
yeah, yeah.
So
Well,
really, punchline, as I said, is that it's not defined.
yeah, because like any local sequence would be lambda complete if lambda has countable personality. Yeah, but we prove that for the other ordinals we can't say it's a request. Okay. Thank you.
No more questions?
Okay, the talk is finished, the seminar is finished. The next Friday there will be another talk, it will be announced in time. And now you close the section. Okay.
I will now stop recording.